is the D1 anode, the D1, oh my god, what am I saying? The D1 diode has the anode at the top and the cathode at the bottom, so it's a forward bias. So we draw the arrow for the voltage like this, and this is VD1, and this has the cathode on the top and the anode on the bottom. So this is reversed biased, and we will draw the arrow like this, VD2. Also, um, we have a current, so we need to draw the arrow for that, and this current goes like this, and this is called ID1. Perfect. Since our second diode is in reverse biased, this whole branch, it's disconnected because the diode is off. It can have two states. It can be on or off. So the first thing you write when you have a problem like this, it's that in our case here, VD1 is bigger than 0 and VD2 is smaller than 0. This is the condition you are aiming to fulfill by the end of the exercise. Excuse me, let me accept some people. All right, perfect. So we can start. I mean, there's not much theory behind it. Since this is disconnected, this is the only loop we can have. This is E. This is 20 volts. E, 20 volts, and we just take a Kirchhoff, this closed loop over here, and we know that E is equal to R2 plus R1. These are basically in series. R2 plus R1 times ID1, the current here, plus VD1. Perfect. We also need to keep in mind he gave us something at the beginning of the homework. I forgot to write. This is the saturation current, and in our case it's 10 picoampere, and we also get an N, which we will use later, which is 1.2. Perfect. We need to find out ID1 from here. So we will rewrite this equation to have ID1 as the unknown we are calculating. So ID1 is equal to E minus VD1 divided by R2 plus R1. So whenever you have a problem like this, there's no way you know VD1. So we're gonna have to make some approximations, and the first approximation we do here is we write VD1 as being equal to 0. So we can calculate this properly. So this results to ID1 being equal to 20 volts, E is equal to 20 volts, divided by 1 kilo ohm plus 2 kilo ohm. So this is 3, and I'm just gonna plug this into the calculator. Also, a very important thing at the exam, please bring a scientific calculator, otherwise you will struggle with these calculations. This is equal to 6.67 milliampere.
If I have a fancier calculator, will he not let
He
me use
does
it?
not care at all.
Okay.
So yeah, this is milliampere because we're dividing volts by kilo ohm. Perfect. We have two formulas to be able to find out VD1. We're going to use the simpler one, which is the one he also used regularly in class. We will completely ignore the second one. For now, it's a lot more complicated. So VD1 is approximately equal to N times KT divided by Q1. This thing over here is the threshold voltage, and some of these things are constants. We're gonna see later. Times ln of ID1, which we calculated earlier, divided by I0. Perfect. This is IS, right? This is, we're gonna write it as 10 to minus 9. Perfect. And this
Who is I0?
Bro,
IS
it's
here.
10 to minus 11, no?
It's 10 to minus 9, I'm pretty sure, no? Or, oh, actually, um, I think I'm making a small mistake here because, or am I? I'm not sure. Yeah, so uh, 10 picoampere is equal to 10 to minus 9 milliamps. We got that out of the way. So yeah, this I0 is this saturation current over here. So we know that N is equal to 1.2, and this over here, KT, I'm gonna write it over here, KT divided by K1 is approximately equal to 25.9 millivolts. Okay, this is a constant. It is always going to be like this. So this results to VD1 is equal to 1.2 times, we're going to rewrite this as 0 0.0025 just for simplicity, times ln of ID1, which we calculated over here. It's 6.67 divided by 10 to minus 9. I'm not gonna write milliamps, whatever.
Why did you write it as 0.025?
For simplicity,
In
you
volt
could.
or in
Isn't it
millivolt?
0.025, just not 0.00?
It depends on what you're converting it to. But 25.9 millivolts is equal to 0.025.
Oh yeah, we use volts. Okay, okay.
Yeah. It's
Sorry.
yeah, just for simplicity. And again, I gotta calculate this.
Filmează careva.
Hmm?
Filmează careva. Te pup, Codruț.
Voi vedeți doar ecranul ăsta, nu?
Da, da.
Ok. 1.2.
Sau trimis după pe grup sau ceva. Sau o pui tu într-un WeTransfer și o pui pe grup.
Da, o să... vorbești cu Codruț.
Cu
Auzi?
cine filmează, da. Sau și astea poți să le pui.
Da, o să fac sesiuni la toate astea și o să le pun pe grup.
Te pup.
Auzi?
Da.
Să știi că I0 este 10 la minus 8, că ai 10 picoamperi și faci 10 ori 10 la minus 9 și 10 la minus 8.
Tu zici că...
Dacă nu e 1 picoamper, sunt 10 picoamperi.
Sunt 10 picoamperi, da. Și în miliamperi, asta vine... Da, ok, 10 la minus 8 sau 1 ori 10 la minus 9.
E 1 ori 10 la minus 8.
1 ori 10 la minus 8, da. Sorry.
Ce faci, calculezi sau?
Da. Ai calculat tu?
Nu, că nu prea sunt într-o locație unde pot să calculez.
Am înțeles.
Auzi, dar nu e 25 de milivolți, nu e 0,025 volți?
Asta e așa, scuze. Stai să pun asta pe calculator.
Da, e un 0 în plus acolo la 0,025. Gen, trebuie să fie 0,025, nu 0,0025.
Care asta de aici?
Da, da.
Deci cât avem? 25,9 milivolți? Da, am
Da,
văzut
vine.
dreptate. Da, vine doar 0,025. Ok.
Și
Și?
ok, dacă avem, presupun că faci și una cu două diode amândouă on state, nu?
Parcă am mai avut ceva similar la temă, nu? Nu știu, eu fac gen ce găsesc în față, nu am nimic stabilit.
Ok, ok.
Am mai calculat cineva? Că mie îmi dă o valoare destul de ciudată. Nu știu, mie mi-a dat I got the result 0.6095 volts.
Întrebare. Tu folosești Wolfgang ăsta alfa? Wolfram alfa pentru a calcula valorile?
Nu, am un calculator științific în față pe care îl folosesc.
Ah, ok.
Well, I'm pretty sure, I mean, according to the calculator, this is the value that we got. So, yeah. I hope it is correct. Right. Next step is we will go back to the ID1 formula and replace this here with the value we got. So we can calculate ID1 with the voltage for VD1 being 0.6095. And we can rewrite it ID1. I'm just going to write it directly, 20 minus 0.6095 divided by, I think it was 3. And this is going to be equal to this is equal to approximately 6.46 milliamps. Good, perfect. So what do we have to do now? We have to so even though we said that the last branch, this one over here is cut off, we still have to calculate VD2. So because we just have to calculate it so we can prove that the diode is off. So we can see if its value is actually smaller than 0 or not. So that is what we are gonna do, and we're gonna take the this Kirchhoff over here. It's basically gonna be R1 times ID1 because we need to get the voltage for the voltage here for this resistor plus VD1. Oh, I'm not on the right page. So again, R1 times ID1 plus VD1 is equal to R3 plus, we are gonna use ID2 here, ID2 Actually, we are not going to use ID2 because this branch is cut off. The current going through it is the saturation current, so it is going to be 10 to minus 8. I'm just going to write it directly. Minus VD2. And we know all the values except this one, so this is just going to be replacing. I don't want to do it anymore because it takes me a lot of time to plug it into the calculator, but it's pretty obvious that this is gonna give us VD2 being
Scuze, am și o întrebare.
da, te rog.
Deci, noi branch-ul acela nu luăm în considerare pentru că e în reverse bias dioda 2, nu?
Da, exact.
Ok, și acum la Kirchhoff am luat R3 ori ES pentru că tot din cauza asta, nu? Că e în reverse bias.
Exact, da. So why we took the saturation current here, it's because this branch is basically, we don't take it into consideration. This diode is off. So this is the current that goes through it. It's very, very, very little.
I have another question. Do we
Because
have to recalculate ID1 again, or the voltage on VD1 again? Because I remember in the homework we had to do it multiple times until.
So from what I remember, there was the table, right, with VD1 and ID1, and you do the approximations like when VD1 is 0, how much is ID1, and for when you get ID1 and you go back and you calculate VD1, right, like let's name this is X, or actually we know the value of it, like 0.6095. If you want to, you could go back and calculate ID1 again. I'm not 100% sure how necessary it is to calculate ID1 twice. In the homework I did it only once and he didn't say anything, but your colleague is right. I think it's better if you do it twice. I'm not sure entirely why he wants us to do it twice. I don't know if there's a reason behind it, but like I told you, I did it only once in the homework and he didn't say anything. Right, so you have to end off this exercise by saying that VD2 is smaller than 0, and then the last thing you write is that VD1 is bigger than 3NKT divided by Q, and this proves that it is on, and VD2 is smaller than minus 3KT divided by Q, which proves that it is off. And this is where the exercise ends. This is a standard thing. You will have to write it. Obviously, there's different cases. Maybe both diodes are on. So you're gonna have to write them both like this. I don't really remember what we had in the homework. So
can you also do one where both diodes are on, so we can
there
see
was one with where both diodes are on. All right, let me go to the
or
homework.
you can just go back and flip D2. So it
you know what? I wanna solve an example of his where both diodes are on, because again, most probably this is what we're gonna get in the exam, right? So it's better to oh, all right, never mind, actually you were right. The second problem is legit this one, just flipped around, my bad. So let's draw it. All right, have the node here, is it not? First diode up R2. Okay. There's a node here. and then this one in parallel with second diode like this. All right, this is R1, this is R2, R3, diode 2, and diode 1 plus E. All right, let's take the following values. We will take we'll write this 1.2. E is equal to 10 volts, R1 is equal to 4 kilo, R2 is equal to 2 kilo, and R3 is also equal to 2 kilo. All right, so as we can see here, the both diodes have the anode on top and the cathode on bottom, so this is called forward bias, right? So you're gonna draw both arrows in this direction, and you're gonna start by declaring that VD1, and you can write a small 2 here as well, are both bigger than 0, which means that they are on. Okay, nice. Let's see what Kirchhoff we can take. We're gonna have to take actually 2 Kirchhoffs here, one for each
loop?
of these branches.
2 loops, right? One
Yeah,
like
yeah.
outside and another one inside the
I mean,
first.
we can take them both like this, and we can write E as being equal to R1, right, the resistor here, times ID1 plus ID2 plus R2 times ID1 plus VD1, right? And this is for the first branch over here. And then for the second branch, we can legit just write the same exact thing, but replace this R2 here with R3 and with ID2, and VD2 here. It's just as correct, and this part stays the same. R1 times ID1 plus ID2 plus R3 ID2 plus VD2. All right. If anyone has any questions, please stop me. I am incredibly tired. I will probably make mistakes. So if you spot anything, if you don't understand something, please say. I really want to help you guys out here. All right. Right. So let's start replacing. This is 10. This is also 10 equal to 4. Yeah, let's write them like this. 4 times ID1 plus 4 times ID2 plus how much was R2? R2 was 2 kilo, so this is gonna be this is gonna be 2 ID1, sorry, plus VD1. Okay, and now for the second one, we will write 4 ID1 plus 4 ID2 plus R3, which is also 2 kilo, ID2 plus VD2. Sorry for the bad handwriting. All I got is a mouse. So again, we're gonna do the same thing we did in the last exercise. We're gonna assume that VD1 and VD2 are both 0. Yeah. Nice. Okay. So we can calculate, we can add up what we have here. So we have 4id1 plus 2id1 plus 4id2. So we have 10 equal to, how much was it again? 6 id1 plus 4 id2. Yeah, 4. Let me do this actually. Okay, plus 4id2, and same thing down below. 10 is equal to 6 id1 plus 4 id2. Great, perfect.
Nu e,
So-
stai, nu e 6x2?
Ba da, așa e.
Da, corect. Okay. Yep, it's 4 id1 plus 6 id2. Okay. What can we do here? So we could multiply by, oh, this is a bit of a situation. Did I make a mistake somewhere? I might have taken the wrong value. Yes, I did. Sorry, so our R2 is 8 kilo here. So this will become, what changes here? This will become 12 id1 plus 4 id2 is equal to 10, right? Because our value is now 8 instead of 2, and 4 id1 plus 6 id2 is also equal to 10. All right, that is a lot better. Why? Because yeah, we can get rid of id1. We will multiply this by -3, and we can then add up the two equations. So we get, this is 0, -3, this is -18, plus 4, this becomes -14 id2 is equal to -20, because -30 plus 10. So we get that id2 is equal to, and let me calculate it.
1.42.
All right, thank you very much. 1.42 milliamps. Perfect. So now we can go back and calculate id1, and we will take the second equation. It has smaller numbers. id1 is equal to 10 minus 6 times 1.42 divided by 4, and this results in id1 being 10 minus 6, 10 minus 8.57 divided by 4. Let me accept some of your colleagues. All right, this will give us
Walid, dar o întrebare. Nu era 10 minus 8, 52?
52 sau 57? Stai că am făcut calculul în cap, deci nu știu.
Nu era 10 minus 6 ori 1,42 supra 4?
Ba da.
Asta e că aici în primul rând avem, sorry, this is 42 and 6 times 1.42 is 8.52. Yeah, sorry. Okay. So this becomes 0.37 milliamps. Okay, nice. So what do we do now? Let's calculate VD1. VD1 is equal to same thing, 1.2 times 0.025 ln of what was ID1? 1.42 divided by 10 to minus 8, and this results in okay, I hope
În logaritm ai luat curentul de la EDAE, la numărătoare, să știi. Ai pus 1,42 în loc de 0,37.
Păi ID1 trebuie să scrie aici, nu? Da, am înțeles ce zici. Sau, mai că putem să lăsăm și luăm pe ăsta ca VD2. It's the same thing. This is VD2 actually because I used the second because I used ID2, and VD1 it's the same 1.2 times 0.025 ln of 0.37 divided by 10 to minus 8. All right, and this will be equal to
Hello, can I ask a question?
yeah, sure.
Please, where is the minus 8 from?
This is the saturation current which we got at the beginning of the problem. It's 10 picoampere, and we just rewrote it as 10 to minus 8.
Oh, okay. Thank you.
No problem. 0.5228. Again, I'm not sure if these calculations are right. Doesn't really matter as long as you apply the right formula. He will give you the points for it. Da, întreabă. Da.
Aici mai dai puțin la imagine, te rog.
Da, sigur, imediat.
Ai spus VD1 și VD2 sunt egal cu 0 ca la ultima problemă. Știu că erau două cazuri, când e mai mare și când e mai mică.
Ce să fie mai mare sau mai mică?
Egal cu 0. VD1 și VD2.
Deci noi, ca să aflăm un ID1 și un ID2 inițiale, trebuie să facem trebuie să facem niște aproximări și luăm astea ca fiind 0 ca să putem să calculăm ID1 și ID2.
Deci pentru simplitate din nou.
Da, deci și asta zice și colegul vostru, adineauri, cred că are dreptate, adică din nou nu sunt 100% sigur, dar după ce calculați al doilea VD2, trebuie să mai calculați în cazul în care avem doar un branch aici, trebuie să calculați încă o dată ID-urile cu acest VD nou, dar eu nu am făcut la temă și a fost ok.
Auzi? Pot să explic eu ce cu tabelul ăla. So about that table, it's called proving the convergence of the solution. And you need to do it because I didn't do it at the homework and he deducted points. So basically, you need to first do the calculations with the VDs being equal to 0. And then after you get to the currents, you need to put them in the table and then redo the calculation with those currents to get new voltages and do this over and over again until you get basically the same precision up to 2 decimal points. You need to get a similar solution to the previous calculations, and that's the real value. That's the final value.
Sorry, did you say you call those tables?
I didn't understand what you said.
Sorry. You said that those tables had a name. Which one was it?
It's this table over here. It looks similar to this.
Yes, doing that is called proving the convergence of the solution. Because basically you're approximating and you need to get as close as possible to the real solution. So you need to redo the calculations over and over again until you get something as precise as you can.
Okay, thank you.
That's very interesting. I didn't know that actually.
Da, mi-a scăzut puncte de la temă.
Da, gen, la mine a fost ok, adică îi făcusem tabelul, nu îl făcusem complet, cum a făcut el la seminar, dar a fost ok, adică cred că...
Câți pași faci până nu mai ți se modifică valorile?
Deci, până vezi că primele 2 decimale sunt la fel ca data trecută, cum ar veni. Și iei doar cu 2 decimale rezultatul final.
De obicei cât durează asta?
Vreo 4 pași.
Ok, și după ce afli VD-urile noi și deci care e procesul?
Deci mai întâi VD-urile.
Deci faci VD-urile cu 0.
Da, le faci 0 și după aia I-urile le afli din Kirchhoff și după aia cu I-urile alea te duci în aproximarea aia cu VD egal cu aia NKT supra Q logaritmic.
După aceea ca să afli I următor ce faci? Ca să afli
bagi alea iarăși în Kirchhoff și după aia iarăși în aia cu logaritmic și după aia iarăși în aia cu Kirchhoff și
ai înțeles? Adică tu mai întâi zici că VD-urile sunt 0, obții curentul, ID1 și ID2, după cu acele ID-uri noi te duci înapoi sau te duci în formulă și calculezi aia cu NKT, asta de aici, da? So guys, this is a really important formula. And așa, și după ce afli VD-urile noi, mai calculezi odată ID-urile, după înapoi VD-ul cu ID-urile noi.
ID-urile le calculezi din Kirchhoff alea noi, nu? Te duci în Kirchhoff și pui VD-ul ălalt în loc de 0.
Deci, da, uite, gen cum am avut aici, în loc să ai 0, pui VD-ul pe care l-ai obținut.
Aha, ok.
So, I think this is it. Since both diodes are on here, it's a much easier process.
Pur și simplu ai intensitate saturation și...
Nu e intensitate, ai grijă, nu e intensitate, că e curent. Eu nu este intensitate.
Da, curent. Ai curent de... Stai puțin că scopi pe aici. Ai curent de saturation și două ori curent de saturation, de fapt, și voltajul e foarte mare, e exact E.
Da, aceea e a doua formă de care ziceam la început. Right, so I think this is it for the diode circuits. We did an example where one is on and one is off, and we did one where both is on. As you saw, the exercise where both diodes are on is a lot easier. If I'm not mistaken here, you do not have to do that table, I think. So
you have to do it every time with diode problems.
Are you sure? Even when both diodes are on?
Completely sure, because you need to get as close as possible to the solution. You're just approximating.
All right. Well, let's draw the table here with
Okay, nice.
Scuze,
I will
o
leave
întrebare.
now. Is someone recording? Is someone recording for the transistor part? Because I
Am
cannot
mai
stay.
zis odată la început că da, ne distrează.
Ok, sorry. Ok, pa,
Da, păi
mulțumesc.
dacă nu ești atent.
Walid, mie mi-arată că apelul se va încheia în 15 minute.
Yeah,
Bine, am și o întrebare, lasă-l pe fotaful. Așa, scuze. Că știe și el când se închide. Așa, scuze că te întrerup. Deci, am o întrebare. Dacă, ipotetic, am avea ambele diode în reverse, adică să fie upside down, s-ar lua cazul tot ca forward bias, nu?
Nu știu dacă avem așa exemplu, gen să fie ambele diode
da,
ambele diode off.
Da, cred că da,
nu,
da.
Nu cred că are cum să le dea, nu cred că are cum să ne dea așa.
Dacă sinus nu prea trece niciun curent, deci n-ai ce să calculezi.
Exact, adică o să ai în ambele saturation current și aia a fost.
Deci una să fie gen să fie una reverse și una forward și cazul în care sunt ambele pornite.
Da, exact.
Ok, am înțeles. Mersi mult.
Bye pentru tine. Any other questions for the diode circuit? Oh yeah, we said we would do the table, and here since both diodes are on, I'm pretty sure we have to do we have to split the table in 4 with VD1, VD2, ID1, and ID2. So when both of these were 0, our currents were ID1 was 0.37 and ID2 was 1.42. All right. And then we have these currents. We have these voltages over here. Make sure you guys put the unit of measurement. Is it's pretty important. So theoretically, I'm pretty sure we would have to calculate these again. 0.632. No, the other one. 0.632 and 0.5228. All right, it's no problem. We'll do another round of calculations. So since we have these new VDs, we will have to go back into these equations over here, and this time replace VD1 and VD2 with our values. So 10 is equal to, actually we can take the, no we can't. So 10 is equal to 4ID1 plus 4ID2 plus 8ID1 plus what's this? Oh, actually, I'm gonna rewrite this because I made a mistake here. If you guys remember, I took the wrong value for the second resistor, so everything should be clear. V1 and 10 is equal to 4ID1 plus 4ID2 plus 2ID2 plus VD2. Nice. So 10 is equal to 12 ID1 plus 4 ID2 plus VD1 0.5228 and 10 is equal to 4 ID1 plus 6 ID2 2 plus 0.632, and this is equal to 10 minus, we're going to say this is approximately equal to 9.48 is equal to 12 ID1 plus 4 ID2, and 10 minus 0.632 equal to 9. I'm gonna approximate it again. 9.37 is equal to 4 ID1 plus 6 ID2, and we will do the exact same thing. We will multiply this by minus 3, and we will add them up. So this is going to be equal to 9.37 times minus 3 minus 28.11 plus 9.48. So this is going to be equal to minus 18.63 is equal to minus 18 plus 4 minus 14 ID2, and minus 18.63 divided by minus 14 is equal to 1 ID2 is equal to 1.33 milliamperes, and we go back and we replace again. So here it's going to be equal to 9.37, 6 times 1.33 minus 9.37, so 1.39 is equal to 4 ID1, which is that ID1 is equal to 0.3475 milliampere. Okay, nice. So we can go back and replace in the formula now with our new currents. VD1 is equal to, I was going to write it directly, 1.2 times 0.025 ln of, where is ID1? 0.3475 divided by 10 to minus 8. And again, let me plug this into the calculator. This will give us 0.5209 volts, and we will do the same for VD2. Right, this will give us 0.5612 volts. And let's write these in the table. 0.5209 and 0.56 and 12. Well, this one's fine, but this one isn't. Nu știu cu cine vorbeam din ori, mi-a spus că
Cu mine ar trebui să pui și ideurile la pașii anteriori. So basically, you can see you're getting closer and closer to the real solution, and you will need to repeat this until you see, for example, at VD1, you can see both last steps have the result 0.52. So that's the real solution probably, but you need to redo it for all values until all of them have the same first two decimals as the previous solution, and that's the real solution. So you need to redo this over and over again until every value on the line has the same two decimals as the first two decimals of the previous.
Unfortunately, 3475.
I mean, I guess you can write like dot, 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 dot. You don't need to really write everything over and over again. Yeah. He will understand what you did, but you do need to calculate it until you get something very close to the last solution.
Yeah, so I will, I think you guys got the idea. I will not continue with this project, it's very annoying. So, yeah, like your colleague said, I hope everyone understood what he was trying to say, because it does make sense. So you need to keep calculating all these values until the first two numbers after the decimal point are equal. As you can see, here is fine, but here it isn't. Here it's close, and here it's close also. So you need to keep repeating this until the first two numbers after the decimal point are equal everywhere, right? And not equal to each other, equal to the previous iteration.
And also, you don't leave it like this with the last with the I columns missing. You need to calculate them for that step as well. And someone asked in chat, yes, you need to have it the same for VD1, VD2, ID1, and ID2 as the previous solution, and that's the final answer.
Right. Thank you very much for that addition. It definitely helped. We found out more new stuff. I will resend a link to the meet. We'll make a new one. Da, spune.
Pe desen, loop-ul l-am văzut de la asta cu două diode în același sens. Trebuie să fie un singur loop? Sau cum contează?
Mie mi se pare așa mai ușor, adică sigur este altă metodă să poți să rezolvi așa, dar mie mi se pare așa cel mai logic și de obicei eu iau primul Kirchhoff pe care îl văd, știi? Asta mi-a sărit în ochi, m-am gândit că pot să fac un sistem așa din ele și calculez VD1, VD2. Dar, din nou, sigur mai este o metodă să poți să faci altceva și tot să fie corect aici.
Înțeles, mersi.
Bun. Cu o plăcere. Alright. Let's I need a yes, please. Please, someone say the
Walid, întrebare. Poți să faci și de la tema 1 un circuit de tipul circuitul 3, de exemplu?
Circuitul 3?
Da.
Stai să mă uit. Da, n-ar trebui să... Da. Chiar cred că despre asta vorbeam.
Mersi.
că asta e simpluț. Ah. Doar doi rezistor? Ciudat. Okay, cred că I think we can start. I think everyone who still wanted to join. Never mind. All right. By the way, if you guys are saying something in chat, I can't see it. So, okay, never mind. Bianca, să știi că eu mă iau după pașii de rezolvare ai lui. Sunt destul de buni, chiar. Ăștia pe care i-a scris la seminar. Nu știu dacă le mai am scrise. Trebuie să văd, dar o să încerc. Okay. Let's start off. I think it's good. Actually, this is R2 and this is R1. We delete that. R1. Okay, so this is ID1. This is the first diode. This is ID2. Write this plus in here, and we will take the values. E is equal to 10 volts. R1 is equal to 0.4 kilo R1, and R2 is equal to 8 kilo ohms. And again, both diodes are on here, so we will write that VD1 bigger than 0, VD2 also bigger than 0. Okay, let's try to think this through. So let me also draw the arrows, this one here and this one here, VD1 and VD2. Good. So let's try to see what is the best Kirchhoff that we can take here. Okay, we can take so R1, I said this was R2, right? R2. Okay, perfect. We could say that E will take this Kirchhoff over here, like this. Okay, so this is E being equal to R2 times ID1, right? Because the current going through here is ID1, plus VD1 plus VD2 all the way until there, VD2. Right. So from here we can take ID1 out, ID1 being equal to E minus VD1 minus VD2 all divided by R2, and same story here. We are gonna take
Scuze că te întrerup. Cum rămâne cu R1?
O să luăm alt Kirchhoff pentru ăla. So for actually, so if I remember correctly, he did something at the seminar. He solved this in a certain way with he took the currents going through here. So he basically took this Kirchhoff. I don't know how to explain. So he took this Kirchhoff over here, and he said that ID1 is equal to ID2, right? Yeah, ID2 plus VD2, VD2 divided by R1. I just wrote it directly. And from this over here, we're gonna have to get ID2. ID2 is equal to ID1, right? ID1 minus VD2 over R1. Okay, great. I'm pretty sure that's how it's supposed to be.
O întrebare. De unde vine VD2 supra R1? De unde ai luat?
VD2 împărțit la R1 pentru că sunt în
paralel.
În paralel, da. Deci așa e.
Intensitate pe R1.
Nu știu dacă
nu e ceva regulă. E pur și simplu Kirchhoff current law în nodul ăla de diode.
Exact.
Pentru că ce intră trebuie să fie egal cu ce iese.
Exact. Da, exact.
Deci intră ID1, iese ID2 și mai iese și curentul care trece prin R1.
Exact.
Și R1 se află, R1 practic se află în paralel cu D2 și de-aia pe R1 se duce tensiunea VD2, deci densitatea este P supra R.
Spune și în engleză, te rog.
So basically in that node between the two diodes, you apply Kirchhoff current law, where the currents that enter the node must be equal to the currents that exit it. And you can see it's not a loop, it's just in the node.
Oh, just in all right, I get it. Yeah,
Kirchhoff 2 is with nodes.
Yeah,
so basically ID1, what enters, is equal to what exits, ID2 first, and then also there is a current going through R1 because there is a voltage on R1 and that voltage is VD2. So the current that goes through R1 is VD2 over R1. That's it.
Yeah, I hope everyone understood this. All right. So we move on. We will have to calculate the currents first. If you'll excuse me just 2 seconds. All right. Let's go back. So we know here the currents ID1 and ID2, the ones that come through here, will be equal, and you can you can get those by simply if we can get ID2 as being equal to was 10 volts divided by 8 kilo, and this will give us 1.25 if I'm not mistaken. And this is also equal to ID1, and like this we can calculate our first VDs, which are actually going to be equal. So since their currents are equal, so we'll just write it directly. 1.2 times 0.025.
Nu prea știu ce faci aici.
Păi,
nu era mai întâi că faci VD1 și VD2 egal cu 0 și după aia le pui în ID1 și ID2 și după aia V-urile cu formula Boolean.
Da, dar deci, așa, pentru că ai poți să afli ID-ul direct. So why I'm doing this and I'm not taking VD1 and VD2 equal as 0 first, it's because you can find the currents directly. We can get the currents. We know that they're equal to 1.25 and we know that they're equal. I think this is the proper way to do it. I mean, we take VD1 and VD2 as equal to 0 because there's no way for us to find out ID1 and ID2 usually. But with this setup, it's easy to find the currents. So there's no reason for us to take them as being equal to 0, VD1 and VD2 as being equal to 0, and then finding the currents and then going back and finding VD. Are sens ce zic? Nu știu dacă ești 100% de acord, simt că nu prea ești 100% de acord.
Bro, can you re-explain the first part really quick?
Which first part?
Like
the Kirchhoff's I took?
Yes.
This is a Kirchhoff. This your colleague explained it. It's the Kirchhoff current law. The Kirchhoffs that with the nodes, the current that enters has to be equal to the ones that equal to the one that
exits. Yes.
That exits. Yeah. So this is where this came from, and this is just the Kirchhoff I took.
But for that one, why is R1 not included?
Because we didn't go... Ne-a dat o valoare diferită la circuitul 3? Sau ce?
Da, eu așa știam. O am scris-o.
Ia, stai circuitul 3 aici, da.
Asta că gen sunt pe
temă... IS-ul nu era 10 PA? IS-ul
Stai așa, scuză-mă. Deci eu sunt pe tema aici și văd că nu am menționat nimic. A zis ceva în clasă, gen, că la circuitul 3 se ia un picoamper?
Asta nu știu.
Noi am luat de pe drive-ul de la CTI și era acolo făcut ăsta, un picoamper.
Atunci, nu știu, probabil a fost tema diferită anul trecut. Habar n-am, dar dacă așa e, hai că o să iau un picoamper, adică nu cred că e atât de mare diferența. So, your colleague is saying this for this circuit number 3, it's 1 picoampere instead of 10 picoamperes. Not that big of a difference, so it's fine. And for this, we will get the value 0.628 volts, which is also equal to VD2 because they have the same current. And yeah, now we can go back and calculate the new currents, ID1 and ID2, knowing the new voltages. It's 10 minus 2 times, if I remember correctly, it's Okay. 10 minus VD1 minus VD2. Actually, yeah, never mind. Minus 0.628 minus 0.628 divided by R2, which is 8 kilo. So this is going to be equal to 10 minus 0.628 divided by 8, 1.093 milliamps. And we'll do the same for ID2. We can write ID2 1.093 milliamps. Actually, not milliamps. Minus VD2 divided by R1 minus VD2, which is 0.628 divided by R1, which is 0.4. This is what?
Minus 0,477.
So this is negative. This is a negative value, which means that for this iteration, for this specific iteration, it will mean that VD2 will give us a negative value, which means that VD2 is off. The diode is off. So we'll go ahead and calculate again. VD1 is equal to 1.2 times 0.025 times 1.093 divided by 10 to minus 9. And this will be equal to...
Ai uitat să pui LN.
Sorry. .624 volts. Nice.
Scuze că te întrerup. Până la urmă trebuie să punem 10 la minus 9 sau la minus 8?
Deci, pentru exercițiile anterioare a fost 10 picoampere valoarea.
Deci depinde de ce valoare ne dă, nu?
Depinde de ce valoare îți dă. Gen, la începutul temei am văzut că scrie 10 picoampere, dar colegul tău a spus că aici s-ar putea să fie 1 picoamper, pentru că
okay.
așa a fost pus în drive. Dar oricum, gen, nu contează atât de mult. Dacă e 10 picoamperi, e 10 la minus 8, dacă e 1 picoamper, e 10 la minus 9. Deci...
Și vreau să mai întreb, ai putea să repeți, te rog, încă o dată cum ai aflat ID2-ul la început prima dată? Că știu că ai pus că sunt egale, dar n-am înțeles formula care ai folosit-o. Gen, de ce au dat egale?
Pentru că aici am luat gen VD2 ca fiind 0 și 0 împărțit la orice e 0 și rămâne doar ID1.
Ok. Mersi.
Da, pentru ce? Ok. 1.2 times 0.025 ln of minus 0.477 divided by 10 to minus 9. All right, this will give us oh, actually never mind, we cannot do this because this logarithm will give us negative, and as we know from math, you cannot take the natural logarithm of a negative number, so we do not calculate VD2 here, and we just say that it is off. We don't calculate it anymore. Okay, so let's draw the table actually now, see where we are at. This is VD1, this is VD2, this is ID1, and this is ID2. When they were both 0, they were both 1.25. And when they were both 0.628 and 0.628, how much were IDs? ID1 was 1.093 and ID2 was minus 0.477, and here we have just 0.624, and here we leave nothing. And again, we have to keep on calculating the currents here, but I'm pretty sure like now it's just a loop, it's an infinite loop. We're just gonna keep calculating stuff the same stuff using the same formula, so it's really irrelevant to keep going. I hope everyone understood how to solve these circuits. Sorry for the little mistakes here and there. And now we will be moving on to transistor circuits. Those are a tad bit tougher, so you're gonna need to concentrate a bit more for those so you can fully understand them. We will be taking a commercial break. I do want to go drink some water.
Me too.
Okay, we can take the first example, the first circuit. So we have the resistor here, node, another resistor in parallel, and the ground right over here. Actually, I will not take one of those examples because I'm pretty sure he'll give a problem in the exam from homework 2 part 2. He's more likely to give those, as they're a bit more complicated, and that's what he usually gives in the exam anyways. And if you understand how to do those, you will understand how to do the simple ones also. So let's take again the first example. Plus VCC and this is plus 12 volts, and resistor A down, node right, we have V out. Okay, the first transistor the second transistor, and we have a node here, goes right. If someone can please tell me what was said in chat.
Could you please also explain later how to solve the type of problem with JFET?
A JFET? You guys don't have JFETs for electronic devices 1. You only have problems with BJTs. So don't worry about those. Those are, I'm pretty sure, only theoretical. They're only included in the theoretical part for this subject at least. I know there were probably some examples which were roaming around, which had JFETs or MOSFETs. I don't remember exactly, but you will not have those. This is ground. Okay, nice, and that's about it. And we'll take A as being 4K. We'll take B as being 20K. We'll take C as also being 20K, and we'll take D as being 5K. Okay, nice. So some important things to note about.
But where are B, C, and D? Because you don't put the letters on the resistors.
Oh,
except the first one.
This is D. This is C. This is B. This is Q2. This is Q1, and this is just a capacitor. 10 microfarads, and oh, here it's VEE. This is minus 12 volts. This V and this V out, and I think that's it. Okay. Some important things to note about BJTs. It's the fact that this is called the base. This right here is called the base. This is the collector, and this is the emitter. So across this down here, we have the voltage between the collector and the emitter. Starting here, we'll put it here. We have the current going through the collector. We'll write this as IC2, and this goes down here. This we will not name IE2, we will name as IC1, and I will explain why, and this we can write as IE1. So basically, the current that goes through the collector is approximately equal to the one that goes into the emitter. So since alright, whatever, he likes to put them in a circle. I don't know why, but whatever. So the current that goes through the collector is equivalent to the one going through the emitter, and since these two are in series, means they will have the same currents everywhere. So IC1, IE1. Alright, perfect. We also you also know the values beta is equal to 100 and VBE, the voltage between the base and the emitter, it's equal to 0.6 volts. Again, this is approximately 0.6 volts, and this value is almost it's always the same, these two. Okay. So we will start. What we have to find out here, it's exactly like what he put in his algorithm, which he did post on Moodle. If you guys go on homework 2 part 2 second run and scroll down, you will see that he took pictures of the blackboard and he posted them, and they have everything there. But yeah, so let's start by applying the Kirchhoffs here. We'll take the first one as being so I'm gonna do this. So A is we'll name this as R1, we'll name this as R2, we'll name this as R3, and this one as R4. Okay, perfect. So we could take this one over here, be we could go as VE R4I. Yeah, I'm pretty sure we could take this. We can take this Kirchhoff over here. Right, all the way to minus 12 volts. And this will be equal to VEE is equal to R2I plus R4I. The current will be equal between them as they are in series. Yeah, ask.
Where is IE2?
IE2, this is what I explained. So we will not write IE2 on the circuit. We will write directly IC1, the current going through collector of the first transistor. But if you want, if it's easier, I'll just write
okay,
this.
so it's the same.
Yeah, this
Okay,
is...
perfect.
Oh, also one thing you have to write at the beginning of the problem is you have to write this supposition. Suppose that IC divided by beta is much smaller than I. Okay. Perfect. We can go on now. So from this we can... Okay, we have 15 minutes left on the call. That's crazy. I is equal to VEE divided by R3 R2 plus R4, and this is gonna be equal to minus 12 volts divided by R2, which is 20. Oh, this is just 40, and this value is gonna be, this is this here, when we move it to the other side, it's gonna be minus no, it was, never mind, it was good. So this is when you first take this Kirchhoff, you're supposed to write it as minus VEE plus R2 I plus R4I equals 0. This is how you use.
Please, I have a question.
Yeah.
Please, why did you take D instead of C? Because the kickoff shows it passes through D, through C before D.
No, it goes B, C, and like it goes from here until this VEE over here. This
But
is
you didn't
actually
write,
VE.
but you didn't write C in your equation.
Excuse me?
But you didn't include C in your equation.
C is R3.
Okay.
Yeah,
not in the
Este este 4.
Yeah, wait,
it's not in the VEE equation you're writing.
Sorry?
like look,
No,
it
I
goes
didn't get
from B, C, and then it goes down.
Ai pus
Oh,
R4
okay.
în loc de R3.
This is D and this is C. I just looked over and apparently he switched them, and this is how
Oh, okay, now it makes sense.
I think
Okay.
it's supposed to be. Yeah,
Yeah.
it should be better now. Sorry. Yeah, so this is this over here is minus VEE, right? This is minus 12 volts. So when you take when you first take the equation, you write it as minus VEE. That's why when we move it to the other side, it's just VEE, it's plus VEE. Okay, so when we take this is going to be equal to plus 12 divided by 40, which is 2 seconds, 0.3 milliamperes.
Why is it 40? Isn't it 25K?
No, because it's B plus B plus C. B plus C. And I should rewrite this. Yeah, no, it's actually right. R2 and R. What this is C.
Yeah, it's 25. It's supposed to be 25.
Yeah.
Because
Yes,
it's
it's supposed to
20
be-
plus
yeah,
5.
yeah. Sorry, yeah. B. Let me make sure I wrote them right. A B C. Yeah, A B C D. Yeah. So B is. I hate the fact that he put letters here. Like, why did he do that? Okay. B is R2, C is R4, so this is supposed to be 25. And 12 divided by 25 is 0.48. Milliamps. All right. We move on. So that was the first Kirchhoff, and we found out. I'm gonna actually screenshot this so we can have it on the next page. Okay.
Am și o întrebare.
Te rog.
De ce luăm doar R2 și R4 în chestia asta? Adică de ce luăm doar...
Păi ca să aflăm curentul pentru B și C aici. Și asta pleacă de la ground la minus VE. Vine
Deci,
fix așa.
Noi luăm de la ground la...
Deci tu trebuie să iei... deci trebuie să fie Kirchhoff-ul tău să înceapă de la zi. Ce-mi scapă? De la zi, un loc unde intră potențial și un loc unde iese. Știu că aici este puțin confuziat că am luat de la ground la minus VI, dar aici putem să considerăm el oricum trebuie să meargă de undeva până la ground. Și aici am luat de la ground până la minus VEE.
Am
Nu știu
înțeles.
dacă are complet sens. Da? Pentru că, adică de-aia am făcut egal cu 0. Ground-ul este egal cu 0 și VE-ul nostru e minus 12. Asta era cel mai ușor ca să poți să afli curentul care merge prin B și C. Da, deci țineți minte mereu că când luați un Kirchhoff din asta care nu este într-un loop închis, trebuie să meargă, trebuie să ajungă mereu în ground. În cazul ăsta, la noi a plecat la ground. Nu contează dacă pleacă de la ground sau se termină în ground, dar trebuie să fie un ground pe acolo, trebuie să fie un 0.
Și vreau și eu să întreb ceva. Acel IC supra beta n-ar fi trebuit pus pe desen ca curentul în bază?
Da. Nu e 100% nu e obligatoriu.
Da, și încă o chestie, că la probleme pe care le-am rezolvat nu era așa, puneam IC1, IC2 pe beta la ambii tranzistori, aici primul tranzistor e la ground, deci nu se pune nimic. Că mă uit la asta pe run 2, unde a pus poze cu tabla și nu a pus pe la ăla de sus, că cred că pentru că e la ground, deci e 0 curent.
Da. Asta zic, gen, nu, înțeleg ce zici, dar asta e doar un supoziție, gen, e la pur și simplu zice suppose that și le pune pe desen. Nu e obligatoriu să-l pui.
Pe general ai curentul bazei.
Știu, e curentul care intră în bază, dar curentul ăla e atât de mic, ai putea spune că e neglijabil. Dacă nu îl pui pe desen, să știi că nu îți face nimic, nu zice absolut nimic. Nu e obligatoriu.
Da, văd aici pe rezolvarea lui, deci mai întâi a spus că definește IC1 și IC2 și după aia la 2 suppose doar IC1 pe beta mai mic decât I.
Da, aici, ok, nu am pus unul. Da, aici ar trebui să fie doar IC1. Nu sunt ambele IC1 și IC2. So you don't write for both transistors here that IC over beta is much smaller than I. It's just this one over here.
Because the base of the first one is connected to ground.
So
for other problems, you need to write.
Yeah, right. If we did not have for the first transistor here the base connected to the ground, we would have wrote that both IC1 and IC2 divided by beta is much smaller than I. Ok. Dar, da, să știi că nu e obligatoriu să le pui pe schemă. Asta știu pentru că l-am întrebat pe el personal dacă trebuie să le punem de fiecare dată când desenăm schema DC. Also, one thing, he might ask you to draw, I highly doubt it, but he might ask you to draw the DC scheme. And for the DC scheme, you don't. Sorry, no. That's what I'm saying. He might ask you for the DC scheme, not like besides the AC one. He might ask for the DC, and the DC scheme is simple. It's the exact same drawing, but any capacitor you see and any load resistance you exclude it. So, for example, here, this would just become a wire. And we would not have this capacitor anymore. And also any voltage generator which you see, you do not draw in the DC scheme. I don't think he will ask for it, but if he does, it's a pretty easy thing. You know how to draw it. Yeah. So no capacitors, no load resistance, no voltage generators. Yeah. These three things you exclude from the DC scheme. All right.
Am și o întrebare, dacă poți clarifica.
Da.
Pe loop-ul pe care l-ai luat, cred că mai mult suntem confuzi. Cum se procedează cu voltaj negativ și cu de unde până unde e voltajul, unde pleacă, unde se termină, cum se scrie ecuația corect, cu semnul?
Deci asta este ecuația inițială. Da, deci asta, Kirchhoff-ul tău pleacă de la minus VEE. Da? Deci de la minus VEE ia path-ul ăsta de aici, se duce în ambele rezistoare și iese prin ground pe aici. Tu ai mai fi putut să iei unul, dar nu știi potențialul între collector și base. Ai fi putut să te duci gen așa.
Proful
Nu,
parcă a zis că n-ai voie să iei între colector și bază.
da, exact, nu, gen, nu ai cum. Nu, ar trebui să stai să faci o grămadă de calcule în plus.
Cred că se lua VC și apoi
Adică
VB pe minus.
crede-mă că sunt o grămadă de path pe care poți să le iei ca să găsești o chestie anumită. Tu ar trebui pur și simplu să o iei mereu pe cea mai ușoară și cred că confuzia vine de la faptul că nu știați că un Kirchhoff poate să înceapă de la minus VI. Dar un Kirchhoff poate să înceapă și de la minus VI și să se termine în ground. Sau poate să înceapă de la VCC și să se termine în ground. Da? Adică nu e obligatoriu să înceapă mereu de la plus 12 volți. Asta nu știu dacă e o chestie pe care a menționat-o domnul Neculoiu, dar eu o știu de la EDAE. De acolo vine chestia asta. Sper că e clar. Îmi pare rău. Adică eu încerc să fac chestii să pară cât mai ușoare, să nu vă complic cu ceva, dar dacă simțiți că vă complic, cu adevărat îmi ziceți și facem cum a făcut și el. Okay. Let's move on and let's find this IC this IC, IE, whatever, all four of these currents, and let's see what the best Kirchhoff would be here. So all right, we could take a closed loop Kirchhoff, if I am not mistaken. We could take
Walid, scuze,
Da.
nu vreau să te întreb, dar se încheie în 2 minute și cred că decât să fie în mijlocul unei explicații
Da, într-adevăr.
îmi pare
Stai
rău.
așa. Nu, e nimic, stai liniștită, chiar îți mulțumesc. Deci, Google Meets. Bro, what are you doing? Okay. Ah, în sfârșit, gata. Now anyone can join without me having to accept.
Sorry, one question. It's more of a general question for the exam, but did the professor say like anything that will be asked in the exam, or
Specifically, no, but like he said, what we're gonna have is one circuit with diodes and one with transistors. And for the theory, it's just standard theory. There's not that many things he can give, but
Okay, perfect. Thank you. And the theory we just study via the the slides that he gave us.
Yeah.
Okay.
Actually, actually no. I have a summary made for the theory, so I'm gonna send you guys that, and you can just study off of it because it's very well structured. It's efficient.
Thank you very much, man.
No problem. All right. Going back to our problem, to find the current going through this over here, to find the current actually, sorry, going through um, the collector and the emitter of the first transistor, which will automatically give us the current going through the collector and the emitter of the second transistor. We can take this closed loop Kirchhoff over here, which will go like this. This right here is VBE1, and it will go like this. It will go VBE1 IE1 no, actually this, what do we call this? What is D? D is R3. Yeah, we can say R3 IE1. Okay, so let's write it. It is IC1 is equal to R4, right? If I remember correctly, C was R4. R4I, which we found out, minus VBE1 divided by D was R3, I think. Yeah, because the voltage of this resistor is IC1 times R3. So this is why we divide everything by R3. And this is going to be equal to, I do not remember the values. R4 is 5 and R3 is 20. So 5 times, oh, we need the current also. The current is 0.48 minus 0.6 divided by R3, which was 20. Okay, this is equal to 0.09 milliamps, and this results that IC1 equal IC2 equal IE1 equal IE2 equal 0.09 milliamps. Okay, great. Actually, did I R3 20K? Yeah, it's good. IC1D. Yeah, nice. Okay, what do we still need to find? Oh, we need to find the, of course, the potential between the collector and the emitter for each one. So let's see. What loop can we take here so we can find VCE1? This is VCE1. We could
Isn't it VCE2?
well, oh yeah, VCE2, yeah. Sorry. Okay, we could take the R2B like this. This is VBE. Actually, no, never mind. I think it would be easier if we went down like this and we found VCE for the first transistor first. So yeah, we could take this path. So this is the trickiest part about these circuits, is you have to find the optimal path to get your calculations right. So yeah, we could take this path over here where we take VBE2 and we go to VCE2 and then we come back here and we get another closed loop Kirchhoff, this over here, and we'll also have to take R2 times I. VEB and VBE are equal. It doesn't matter the order which we take it in. It doesn't matter if it's like this or like this. They will it will still be 0.6. So let's take the Kirchhoff. It's going to be equal to VCE1 is equal to R2I. I think resistor B was R2 plus VBE2 minus VBE1. Okay, perfect. So this results that VCE1, these two will cancel out because they're both 0.6. This will be equal to VCE1 is equal to R2, which was R2, which is 20K and 0.48. So 20 times 0.48 is equal to
9.6. 9,6.
9.6 volts. Okay. Oh yeah, and since this is bigger than VBE, it's forward active region, so it's as he likes to write on the board. Okay, far. Perfect. We also have to calculate VCE2, this over here, and I'm pretty sure now it's easy. We can just take a path from VCC all the way to VEE. It's gonna be a long path, but it's easy. We know all the values, so let's write it first. VCC minus what was A was R1, right? R1, no, equal to R1. R1 IC2 plus VCE2, because that's what we want to find out, plus VCE1. So if someone couldn't already tell, this is the loop we're taking all the way to VEE, from VCC to minus VEE, yeah, plus VCE1 plus this was D, so R3 R3 IE1 minus VEE. because this is minus. So we will rearrange everything so we can get VCE as the unknown, VCE2. This is equal to VCC minus VCC minus R1 IC2 minus VCU1 minus R3 IE1 plus VE. All right, I'm sure this is going to give us an interesting value, and I'm sure it's going to be larger than VBE2 also. This is larger than VBE1. Okay, I think this is it for the DC operational point. So some things to go over again. What we are aiming to calculate is the current going, so IC IB for each transistor, VCE, and that's it. You have to find out the currents, you have to find out the voltage going through collector emitter, and everything else you find is just so it helps you get to these results. But there's no way around it. I mean, you're never gonna get an exercise where all you're gonna calculate is these values directly. He will make the circuits in such way where you will have to calculate other things first and then get to these. Okay.
Can you please explain again how did you thought of the loop for VCE1? What is the path
VCE1
for that?
Oh no, which one? VCE1. VCE1 R2. So we took this is VCE1. Yeah, so we went like this, like this, like this, and like this. Yeah, so it went VCE1, VEB1, VB, and VBE2. Yeah, it's a closed loop over here.
Okay.
Și am și eu două întrebări. Unul la mână putem să facem și desenul ăla?
Stai așa, scuze. Stai așa că primisem un telefon.
Stai liniște.
Așa, scuze.
Putem să facem un exemplu de desen? Just in case, dacă ne... De la,
un exemplu de
la... Doamne, circuitul direct, să nu fie AC, gen ăla, desenul ăla pe care l-a făcut pe tablou, pe care eu nu l-am înțeles. Ăla fără capacitors și fără așa mai departe.
Gen să facem...
Da, pentru ăsta.
Circuitul
să avem un exemplu.
Uite, aici nu o să se schimbe absolut nimic. Sau nu că nu o să se schimbe absolut nimic, scuze. Dar gen, ștergi acest condensator.
Ok.
Și pur și simplu desenezi un wire. În cazul ăsta, doar asta se schimbă. Da?
Am făcut un desen care... nu știu. Stai că sunt în teme. Nu știu, era o linie întreagă.
Nu, adică exact cum am zis, singurele chestii care dispar în schema DC sunt condensatoarele, load resistance-ul dacă este, dar de obicei load resistance-ul este conectat la condensator și voltage generator, adică un voltage generator, de exemplu, putea să fie aici. E pur și simplu desenai un fir în loc să lași acel voltage generator acolo.
Ok.
Cam asta e schema.
Uite, stai, poți să te uiți un pic pe WhatsApp?
Da, pot.
Acum.
Da.